Okay, so with this, I will be, so my name is Panos, Christakoglou, and I will be guiding you through some of the latest experimental results in the field of heavy ions. I will be discussing with you where we stand at this moment, and I'll also close by mentioning what are the opportunities and where the field is heading in the near, but also not so near future. Now, in doing so, I'll be giving a very brief introduction, because I was told that not only at least people related to the heavy ion physics program will be connected. So I'll try to give you some idea in the first part of the talk of what we are doing. And then I'll try to focus on one single measurement that I lately was involved in, and try to illustrate you how things evolve. What is a physics message, and how things evolve in terms of also modeling and where we stand. Okay, now allow me first to remind you that what we try to do in this field is to answer a fundamental question, the one related to how QCT matter behaves at extreme conditions of energy density and temperature. In fact, this is one of the questions that ended up in a list that was defined by a rather diverse committee formed by the National Research Council in the United States. They met back in the fall of 1999, so before the start of this century, and they defined this list of what they called 11 unanswered questions that the high energy physics and astronomy community plan to address in the century that we were about to enter. Now, how matter behaves under extreme conditions is not really a question that people started thinking only in the 21st century. In fact, even back in 1950, one could see that people like Enrico Fermi, with his studies, stimulated these thoughts and ideas that ended up in one of his manuscripts. And soon after, Hagedorn introduced in one of his studies the idea of fireballs when hadronic matter is compressed. Some 10 years later or so, Lee and Wick discussed what they called abnormal matter, while the possibility of finding such a state of matter in the interior of neutron stars was first discussed by Collins and Perry, and followed by what I believe is the first discussion of a deconfined state in the paper by Cabibbo and Parisi. Now, let me just clarify that the initial expectation for such a state of matter was that it would consist of weakly coupled quarks and gluons. Now, this state of matter was coined as the quark-gluon plasma, or QGP. You will hear me using this term throughout my talk, in a textbook paper by Shuriak. And this QCP has been the focus of many theoretical attempts, with lattice QCT calculations providing us with solid guidance for the study of what we call the strong phase transition in the laboratory. Now, within the lattice QCT community, there is since quite some time a common effort to converge on the tools, the techniques, and the configuration used to obtain reliable results. And based on one of the latest such efforts from the so-called hot QCT collaboration, one can see that there is a rapid rise in things like the pressure, the energy density, the entropy density, divided by the relevant powers of temperature as a function of temperature, happening at around 155, 156 MeV or so. So this signals a change in the effective degrees of freedom, and actually signals the transition from a state of matter on the right-hand side, where quarks and gluons are not anymore confined inside their hadronic bags, to the confined world, to the world where hadrons are the relevant degrees of freedom on the left-hand side for lower temperatures. Now, this phase transition happens to take place, or at least this is what theory tells us, at around 155 MeV and at an energy density of around 0.5 GeV over cubic Fermi. And these are conditions that can be accessed and studied in a controlled way in the laboratory by colliding heavy ions accelerated at very high energies. Now, this transition that I was talking about for low values of baryochemical potential for, let's say, for a system with vanishing net baryon number is expected to be a smooth crossover, and this is relevant for the LHC. Now, the state of matter has been the focus of an intense and rather versatile experimental program throughout the last 4 decades, or even more, actually. And in fact, back in 2000, CERN has announced that there were compelling evidence coming from the SPS heavy ion program. So where, as Chia said, my previous experiment was part of, NE49. So there were compelling evidence about the existence of the quark plasma. However, it is fair to say that detailed studies of the QGP and its properties came from another heavy ion physics program and accelerator across the Atlantic, the one at the Brookhaven National Laboratory, or BNL, and its relativistic heavy ion collider, or briefly RHIC. Now, based on studies of the suppression of high transverse momentum particles and jets, also known as jet quenching, and this is something that, due to time, I'm not going to address today, but also on studies on anisotropic flow, and in particular of elliptic flow, and this would be the main focus of my presentation. People realize that the system, the matter which is created after a heavy ion collision, behaves as a liquid, and in fact as an almost perfect liquid. Now, this anisotropic flow that I mentioned before is a phenomenon that reflects the transfer of the initial special anisotropy, so the anisotropy in coordinate space, into anisotropy in momentum space. And you see here the two plots, the one, so coming mainly from simulations that show the time evolution of on the left-hand side of the anisotropies in coordinate space, where you do start with a rather anisotropic system. So depending on how your ions collide, depending on the value of the impact parameter, the line that connects the center of the centers of the two nuclei. So you do have different geometries. For large values of impact parameter, you have this ellipsoidal shape in the overlap region between the two ions. And you see that with time, this initial special anisotropy fades out. And at the end of the day, in coordinate space, you do have a rather isotropic system. So this initial special anisotropy is characterized by the so-called eccentricity. Now, at the same time, you have also the translation of this anisotropy momentum space, which is characterized by the corresponding momentum eccentricity defined by the different components of the energy momentum tensor. And you see that initially, so with time, you do have, well, you start having no components in the transverse plane. So you have an isotropic, let's say, system, and then soon it picks up anisotropy. And by the time the particles are emitted, freeze out and are emitted to our detectors and are detected by our detectors setup, then you do have a significant anisotropy in momentum space. So this latter is characterized by Fourier expansion, the coefficients of which, this Vn, are called the flow coefficient, with the second one, V2, called the elliptic flow, which is the dominant coefficient and characterizes this ellipticity in coordinate space, which is translated into this ellipticity momentum space. Now, so through studies of anisotropic flow, but also of jet quenching, but not only, we have established a rather clear picture of how a heavy ion collision evolves. You do have, at the very initial state, you have two nuclei which are Lorentz contracted, And depending on the value of the impact parameter, I mean, as I mentioned before, this is the line that connects the centers of the two nuclei. You do form different geometries, and these different geometries are also reflected in the final state. Now, initially, so this overlap region turns out to be quite of an ellipsoidal shape, and this actually drives quite a lot of things in the final state that we see. Now, with this, allow me to open a very brief parenthesis, because I did mention this idea about the impact parameter, which to us experimentalists and particularly to heavy ion people is connected to what we call centrality. And this is something that some of you might not be fully, let's say, familiar with. So let me start by saying that obviously heavy ions are not point-like objects. So they do contain, so for the case of lead ions that we use at the LHC, we have 208 nucleons, protons, 82 protons, and the rest are neutrons. Now, the collisions that we have can create systems with different properties, depending on whether they are head-on over here, or so, which is defined by a small value of impact parameter, or with increasing impact parameter, then we discuss about semi-central or peripheral collisions. Now, this impact parameter is not something that we can access experimentally. Instead, how we try to gauge this so-called centrality is by, for example, measuring the number of particles which are being generated after such a collision. So you see on the bottom of this slide, you see some artistic like event displays, where every single line that you see here is a particle track, which is reconstructed by our detectors, by our central detectors. And you see that for the case of a head-on collision for practically zero impact parameter, so you do have a large number of particles which are generated, and then progressively, when you increase the value of this impact parameter, you are able to produce, so the overlap region becomes smaller and smaller, more ellipsoidal in shape, and the number of particles which are being generated becomes progressively smaller and smaller. Now, even if it is small at peripheral collisions, so it's by far larger than a typical multiplicity which is being generated in a proton-proton collision at the LHC, which on average is of the order of 5, 6, 7, up to 10. Okay. Now over here, so for central heavy ion collisions, for example, in the central rapidity region where our detectors are located, we produce more than 2,000 particles per event. So if you integrate it over the entire phase space, you produce more than 20, maybe even 30,000 particles. Okay, good. Now with this, let me go back to discussing about the evolution of a heavy ion collision. So after these two ions collide, then we have what we call the initial stage of a heavy ion collision, which is characterized by the lumpiness of the initial energy density profile. This is the result of quantum fluctuations in the position of the nucleons inside the nuclei. At the same time, you have both soft and hard processes, which provide the means for a rapid thermalization of the medium within the first Fermi over C. Now, after this stage, a strongly coupled liquid, the coagulum plasma, is formed with a very small mean free path. Now the medium expands explosively outwards, an expansion which is driven by the non-uniform energy distribution in the initial state in coordinate space, as we discussed before. And this creates pressure gradients in the QGP stage. Now the evolution of the QGP is described by hydrodynamical models that usually employ viscous corrections as reflected in transport coefficients such as the specific shear and bulk viscosity, and these are terms that I'm going to come back to later in my talk. Now, after this stage, the parts of the QGP that cool below the deconfined temperature will hadronize. They produce a gas of hadrons mainly pions, but also kaons, protons, and other heavier hadronic states which are formed. Now, these hadrons, they do interact with each other, and these processes are usually described by what we call hadronic afterburners. I just give you a name of one who you normally use, which is URQMD. Now, in addition to these hadronic probes, we have hard processes that usually occur at the initial stage, such as the creation of charm and, in general, heavy flavors, so beauty also. So you have also energetic quarks and gluons. They do fragment and create spray of hadrons, which we call jets. And these jets, they do interact with the medium, and they lose energy. They spread their energy. I mean, the energy is not lost, but it's recovered by for example, soft radiation. And you do have, so this energy loss can be of radiative nature, so through inelastic collisions, or you can have elastic collisions. So then we talk about collisional energy loss. Now, at the end, you do have all these particles which emerge from the interaction region, and that they're picked up by our detectors. Now, let me start from the initial state, and that will be the main focus of my presentation. So starting from this, a few years ago, it was realized that actually the position of the nucleons participating in a collision is not constant. It does fluctuate from event to event. And these fluctuations can be calculated from different models that attempt to describe the initial state of a heavy ion collision. And even up to this moment, they constitute, if not the largest, one of the large parts of the uncertainty when experimental data are compared with theory calculations. Now, these fluctuations in the position of these nucleons are transferred through the low viscosity quark-gluon plasma into final state momentum anisotropies. And this is reflected in the development of higher harmonics, even odd harmonics, which, if these fluctuations were not there, if there was initially a system which was fully symmetric, these odd harmonics would not be there. And you see that these things are reflected also in non-zero values of V2. So this is the Vn as a function of the harmonics. So V2, the elliptic flow, V3, triangular flow, quadrangular flow, pentangular flow, and so on and so forth, for ultra-central heavy ion collisions at the LHC. So really head-on collision. The impact parameter is practically very close to zero. Now, due to the fact that these fluctuations, so these flow harmonics, they do represent and probe modulations in smaller spatial scales, they are unique tools to constrain the initial state. Now, how can we measure this? How can we measure these fluctuations? So the question is, what is the underlying probability distribution function, or PDF, of these flow harmonics? Now, if we focus on the second flow harmonic, which, as I said, is the dominant one, but no matter what the harmonic, so you have two ways of measuring this, either via cumulants or measuring this V2 or V3 or V4 on an event-by-event basis. And this is actually what was done at the LHC. And you see here on the left-hand side plot how V2, the elliptic flow, develops as a function of centrality for two energies. So lower LHC energy with open markers, and the highest LHC energy with the field markers. And you see clearly that, first of all, if you compare the two energies, there is no drastic increase in the value of V2, which is to be expected. And however, what is unique here is the difference that you see, the formation of two bands. The upper part, these are measurements performed with two particles. So this is a measurement that can be performed with two particles or with multi-particle techniques. And this latter, the multi-particle techniques, give results which are significantly lower. And this is also very well understood because and this comes from initial state fluctuation, from how Vn, how the eccentricity fluctuates from event to event. And this is also translated into a fluctuation in V2. So if you measure actually V2 with two particles, then you probe the average value of V2 plus the fluctuations. But these fluctuations for the two particle correlation comes with a positive sign. And at the same time, if you measure the fluctuation, so V2 with 4, 6, or 8 particle correlations, so you probe the average value, but also the fluctuations that if you analytically write down how this thing comes about, these fluctuations do come with a negative sign. And this brings this explains the difference that you see here. So the difference that you see, provided that you reduce non-flow contributions. So non-flow are correlations which are not related to the common expansion of the medium. So imagine, for example, having a rho zero that decays into a pi plus pi minus. So this pi plus pi minus would be correlated mainly because of the fact that they come from the same mother, from the rho zero. And so if you reduce this non-flow contribution, then the difference here can be explained very well just by the fact that the fluctuations contribute with a positive and a negative sign when measured, when V2 is measured with 2 or 4, 6, and 8 particle correlations. At the same time, you can also measure the V2 on an event-by-event basis. And this is what CMS did for various centrality intervals. So for kind of central events and then peripheral events on the right-hand side. And it turns out that the PDF that describes the data more is what is called the elliptic power distribution that allows finite skewness, which develops more for more peripheral collisions. So you see here. So these are measurements that are mainly done for charged particles. Okay, so this is something that was not done for different particle species. And back in, when was this? Even before the quark matter of Wuhan, slightly before. So we had a discussion with Huichao and Wenbin. And so we asked them to provide us with their expectation about such fluctuations for different particle species. And they were kind enough to send us these plots. So the plots here show this F, and this F is defined as the measure of the fluctuation divided by the average value of Vn. So it's the relative fluctuations, in other words, as a function of transverse momentum of particles for different particle species, for pions, kens, and protons. And what you see on the left-hand side are kind of central events, so with small value of impact parameter, and some peripheral centrality class, 30 to 40% on the right-hand side. Now, forgive me because I started discussing, so if there are any questions, feel free to interact with me at any given moment. Because, I mean, the way I set up my screen, I don't see the chat window. So, Chia, I rely on you to interact.
Yeah, please keep on going, no problem.
So what you see over here is that, particularly for kind of more peripheral collisions, you do start at low values of PT to see some kind of particle species dependence. So you see that these relative fluctuations become significantly more pronounced for protons and then for kaons, and to a less extent for pions, although keep in mind that we stop here at close 0.2 GeV over C. And then the question arises, where does this particle species dependence come about? So where does it come from? Is it due to the initial state? Is it due to the hydro evolution? Or even due to the hadronic rescattering? So what we did here is that we practically looked at a different model for the same centrality now, so for 30 to 40, where we did see this particle species dependence to develop. And because the last part, the hadronic rescattering part, is common in both approaches, So you see that the left-hand side plot doesn't show this particle species dependence at low PT. So most likely the hadron scattering is not responsible for such an effect. So it can be either the initial state or the hydroevolution. So this kind of motivated us to start studying this type of effects also in data, in collision data at the LHC. And this is what we found. What you see here is the V2 as a function of PT for various centrality classes. So these are central events, small value of impact parameter, and then progressively you move to more peripheral events for larger value of impact parameter, where the initial state ellipticity is quite more pronounced. And this V2 now is calculated with 4 particles. So I remind you that this estimation of V2 with 4 particles, the measure of fluctuations comes with a negative sign. Now, what we see here is what I call the same known features seen in this V2-4 measurement. These are known features that we also saw, and we have studied in quite some detail with 2-particle correlation, so with V2-2. And this is mainly, very briefly, the mass ordering at low PT, which, if we have time, I will. So I plan to explain in a bit more detail how it comes about. So you have a crossing at around 2 to 3 GeV, and then you have a particle type grouping at intermediate PT. And I plan to explain how these things come about in the following slides. So let's start with the mass ordering. So what is this mass ordering? So I kind of took some old results on the left-hand side of this slide, and I zoomed in at low PT where this mass ordering is pronounced. So I go before the crossing point that I was talking about. And this mass ordering is nothing else than the observation that the larger the value of V2, so at fixed value of PT, let's say at 1 GeV, the larger the mass of the particle, the lower the value of V2 is. So you see here that you start, so at 1 GeV, you start with the open stars, so these are the Xi's, and then the blue stars, the lambdas, and then the protons, and then the kaons, and then the lightest of the hadrons, the pions. Okay, and you see on the right-hand side plot, these are similar results, although in the heavy flavor sector, that, for example, the black data points that correspond to the V2 measured 4D mesons. So these are mesons which contain a charm quark. So this mass ordering at low PT is very well respected also in the heavy flavor sector. So the larger the value of the mass of the particle, the lower the value of V2 is. And this can be explained by practically radial flow. So the way the quark gluon plasma expands, or let's say radial flow, which quantifies how the quark gluon plasma expands outwards, radially outwards. Embedded, however, in an azimuthally asymmetric environment. So let me try to illustrate how this mass ordering comes about. So, and this I try to do. So people in Alice probably know this very well. So forgive me for this. But if you have any questions, let me know. So I try to illustrate this with a toy model. And what I do here is that I generate particles, pions, and protons, and I sample them from a Boltzmann-like distribution, their transfer momentum spectrum. This is how this transfer momentum spectrum looks like for a velocity boost, the velocity with which particles are boosted, which is small. I illustrated with β1. So if I increase this velocity, because the momentum is nothing else, I mean, it's related to the mass of the particle. So if I increase this velocity, then what you have is a depletion that becomes apparent at low PT. So in other words, I practically give a boost to the low PT part, to every particle. So the low PT particles, they will move from the low PT region to the high PT region. And this will make the the spectrum a bit harder. And this hardness of the momentum spectrum becomes more pronounced the higher the mass is because of the connection with momentum and mass. So if I increase the velocity even more, then my spectrum becomes harder, and mainly for protons, also for pions, but the effect is smaller due to the smaller mass for pions. Now, this is an isotropic environment, and this results into this depletion at low PT and an excess of particles at intermediate high PT, which mainly comes from, which is particle species dependence, becomes more pronounced the higher the mass of the particle is. And this is not something that is present only in my toy model, but this is also something that we measured experimentally. And what you see here is the hardness of the spectrum at the LHC with the red data points relative to the spectrum that you have at lower energies, at RIC, at 200 GeV square root of S, an order of magnitude smaller center of mass energy with the open points. Now, let's move now to an anisotropic initial state. Now, because V2 is nothing else than the relative yield of particles emitted in the short axis in this direction than in that direction, so what we call in-plane versus out-of-plane. So in the in-plane direction, we have larger push, we have larger velocities, we have velocities that push particles in this direction, which are larger. Thus, the spectra in plane will be harder than the spectra out of plane. You will have a larger low PT depletion in plane than out of plane, which will have a particle species dependence. It will be harder, it will be more pronounced for protons than for pions. So if you do this exercise and calculate V2, then you see that you get, for a fixed value of PT, the larger the mass of the particle, the proton, the lower the value of V2 is. So that is for one velocity, for the smaller velocity. If I increase the velocity, this mass ordering, this splitting between those two bands will become even more pronounced because of the larger boost that particles get. And then if I increase it even more, then you get an even more pronounced mass ordering. So this is practically how this mass ordering comes about. It's just an interplay between radial flow and the fact that you start with an ellipsoidal shape. And this is also something that one can see in models such as the MPT that people are probably, Alice people probably are familiar with. So this, I don't want to go into details, but I mean, the only thing that I have to say is that these are two versions of this AMPT, one with string melting that includes partonic interactions, and one with string melting but without any hadronic rescattering phase. And I try to illustrate here how also the hadronic rescattering phase can play a role in the development of radial flow. So without this hadronic rescattering phase, radial flow becomes significantly smaller because, I mean, the hadrons are also interacting and this helps in building up radial flow, even at a later stage. And you see that within this model, this mass ordering, so the hadronic rescattering phase can also contribute significantly to this mass ordering, which develops not only for V2, but also for V3, triangular flow, and V4, quadrangular flow, but also for other harmonics. Now, one way to probe the contribution of this hadronic rescattering phase is by looking at particles whose hadronic cross-section is small. And a particular example is the phi meson. It's an SS bar pair combination. The hadronic rescattering cross-section is small, if not zero. And if this is the case, then the corresponding mass ordering which develops for the phi meson will not be affected by this late stage. At the same time, protons will be affected. Their hadronic rescattering cross-section is quite significant. And you see here that, I mean, there are models that actually predict that this mass ordering at low PT can be broken, and the phi can be an example. And within our current statistical and systematic uncertainty, the one indicated with a bar, the former, and the latter with the box around each data point, you seem to have a hint of such a breaking of the mass ordering, because the mass of the phi is slightly larger than the mass of the proton. And this data point, if the mass ordering would be followed fully, should be below. But I mean, it's at this stage it's compatible, so you cannot say that that there is a breaking of the mass order. Okay, and let me go quickly to the other part I mentioned, so the crossing and the particle type grouping, so which mainly takes place at so beyond the PT range where the mass ordering is visible. So this mass ordering, this particle type grouping, simply it's just an observation. The fact that all the blue data points that I forgot to say that correspond to baryons, so pions, lambdas, xi's, omegas, so cascades that contain also strange quark. And the red data points, these are these are solely mesons, so QQ bar combinations. So you see that at higher PT, so beyond 3 GeV, so the blue data points are grouped together, and the red data points are also grouped together. And in fact, the V2 value of baryons is larger than the V2 value of mesons. So this initiated the idea that this could illustrate the partonic nature of V2, that V2 develops in the partonic stage, and the hadrons inherit the V2, but also the PT of their constituents. So the V2 of the QQ bar combinations for the mesons, and the 3 quarks or 3 antiquarks for the baryons or antibaryons. So, and this is kind of visualized in what is called the NCQ scaling, number of constituent quark scaling picture. And this is nothing else than, you take the previous plot, V2 as a function of PT, and you divide both X and Y axes by the number of constituent quarks, 2 for mesons, 3 for baryons. And then you expect things to fall in one universal line above, let's say, 1 GeV over C. And it turns out that this scaling is rather approximate. So there are things that, so the data points, they do not fall on the same line. However, so within 20%, this NCQ scaling seems to hold. So one thing that I would like to point out here is that it's not that there is this misconception that at the LHC the NCQ scaling is broken while it works at RIC. So this is a complete misconception. We actually showed that at both LHC and RIC, this NCQ scaling, the number of constituent quark scaling, is either broken or holds at the same level, at the level of 20-30%. So there is no difference in energy. So use the verb that you like, holds or breaks, but the level with which it holds or it breaks is practically the same no matter the energy. And this is expected to be, this particle type grouping is expected to be coming from the way particles are produced. So the fact that, you have QQ bar pairs, which are very close to each other in phase space, they combine and they form a meson. And this is practically a naive way of explaining the coalescence mechanism. And the same stands for baryons. And the way this grouping works within the model is illustrated here. So if we focus on, it's again an AMPT plot. It's one of the models that has many stages, one of which is the way particles, describes the way particles are being produced. And the main mechanism in one of the tunes of AMPT, in the string melting one, is what we call quark coalescence, what I briefly, naively described before. You see that in this if we focus on this column, so in the string melting with quark coalescence, so above a given PT, you have all, so the two mesons here, so pi and scanes, but if I also add more mesons, they will follow on the same line. And protons, so they are separated. And if I add also lambdas and xi's, they will also fall on the baryon band here. And this mainly comes from coalescence, which if I switch off by going to what is called the default AMPT version, where the main particle production mechanism is fragmentation, then practically you don't see this grouping, baryon meson grouping at intermediate PT. So within this model, you get qualitatively the same features as in data by including in the intermediate PT region by including coalescence. Now let's focus on fluctuations. So by measuring V2 with 2 particles and V2 with 4 particles, you can calculate the average value of Vn, but also the measure of fluctuations, and you can plot it as a function of PT for the same centrality intervals. So the average value of V2, where you do see practically the same qualitative features as I explained before, the mass ordering at low PT, the particle type grouping at intermediate PT, so baryons versus mesons. Similarly for the measure of fluctuations, so you do have again mass ordering and particle type grouping, so there is nothing new to see here. However, if you form if you calculate the relative fluctuations and plot them as a function of PT for various centrality classes, central down to peripheral, you do have unexpected interesting features. And let me try to guide you through. So first of all, you have the PT dependence, which becomes to be non-monotonic above 30 to 40, so above a threshold. So for peripheral collisions, let's say, you have a minimum of these relative fluctuations. And at higher values of PT, you have higher values of F for baryons than for mesons. So you have these relative fluctuations of baryons which are systematically lower than for mesons between 1 and 3 GeV/c. So you have some kind of particle type grouping, but not in the same PT region as the region I discussed before, where I was discussing about coalescence. So maybe there is a different origin for these two observations, for the relative fluctuations and the way V2 develops in the intermediate PT region. And above 3 GeV/c, you do seem to have some kind of universal band. So there is no separation between baryons and mesons. Now, I told you before that all these measurements are very well described, all the V2, Vn measurements in general. So hydrodynamical models, they do have quite a success in describing how these things develop in data. And this is no surprise that also here for this type of measurements, hydro calculations, they do have quite a success. So I will skip the details of the model, so you can ask me later if you want. What I want you to take as a message here is that the bands which correspond to these hydrodynamical models, they do describe the data points quite well, no matter what the centrality is, central or peripheral collisions. And this is the measurement of V24. But then if we go, this is the measurement of the mean V2, but also the measure of fluctuations. So if we go to these details, so you see that, for example, fluctuations, although the general features are there for the models as well, so we have to admit that if we look at the details, the model does not describe the data well. So describes qualitatively the features, but not quantitatively the data points. Now, no surprise that if we form the relative fluctuations also for models, So they do fail to describe the general features. So this is something that we are in contact with our theory friends and colleagues, and we try to figure out what is the origin of these effects that we see in data, the effects that I discussed before, and how can the hydro calculations be improved such that they also describe this data. Okay, now I try to describe probably in a bit more detail than I should for such a seminar, a couple of specific measurements. Let me try to give you an idea where we stand and where we go. Now, soon after the startup of the LHC, the field has moved away from qualitative studies, and we moved to quantification and constraints of basic components and parameters that characterize the quark-gluon plasma. As an example, you see here how this is one of the first attempts of such an enterprise, how we can constrain the equation of state so that that connects practically the different thermodynamical variables that describe the system that we create after heavy ion collision by using models, and Hume trained the models to describe our data for protons, kaons, and pions, so the spectra, HBT radii that practically tells you how large the system is, but also V2. So this is one of the first attempts for a global fit on data, and this is how well we can. Back in 2015, we were able to constrain the equation of state, or better over here, the speed of sound squared as a function of temperature. Now, all these things have been improved, and in the next couple of slides, I just illustrate the state of the art of such efforts. So this is what is called a Bayesian global analysis, which uses particle yields, mean PT for different particle species, the flow values that I discussed before, down to quadrangular flow, and mean PT fluctuations. Through this, how we can constrain some of the transport coefficients of the quark-gluon plasma, such as the specific shear viscosity and the bulk viscosity. The former practically illustrates or reflects the resistance of different layers of the fluid in velocity gradients, while the bulk viscosity reflects the resistance in the expansion that the quark-gluon plasma tries to do. This was mainly something, so an attempt to fit only LHC data, but there are also attempts to unify everything into one common picture. So both LHC data, but also using rig data. And this is done under the umbrella of the so-called Jetscape collaboration, which is able to give a coherent physics description of experimental data at various energies from a single model with a common set of parameters, except maybe with a initial energy density. Now, however, the heavy ion physics program, so in general, the heavy ion physics program is not focused only on heavy ion. So we also look actively, and since 2010, we look even more actively in small collision systems. So at the LHC, we collide not only lead on lead, but also proton on lead, but also proton on proton. And already in 2010, we were able to see effects in PP collisions at 7 TeV, so CMS reported it first, that resemble the ones that we see in heavy ions. So I didn't discuss about these plots. So these are angular differences in the longitudinal direction and in the transverse plane, delta eta and delta phi, azimuthal angle, between two particles. And you see that the structure that develops at delta phi 0, which is elongated. So this is what we call the near side ridge, which was mainly seen in heavy ions, and it's part of the decomposition of the evolution of the system in terms of Fourier harmonics. Now in heavy ions, this is how we explain it, but we also see this now developing in high multiplicity proton-proton collisions. But not only this, but we also see that what I discussed before in detail, so the mass ordering and the particle type grouping developing not only in lead-lead, in heavy ions, but also in P-lead this time, from both ALICE and CMS. And as my compatriot Heraclitus used to say, it seems that tapadari, which means everything flows. So I will skip this due to time. So this describes a very textbook measurement done at RIC in order to understand where these effects that we see in small systems that resemble the ones that we see in large systems, where do they come from? Do they come from the initial state? Do they come from the final state? Do we create a QGP droplet even for small systems? It seems that overall the take-home message is that mainly, if not only, hydrodynamical models are able to describe so far the experimental measurements, which points to probably the fact that we create such a deconfined state of matter also in high multiplicity PP and P-lead collisions. So overall, I hope I illustrate you that we did have a lot of progress in with years. So where do we go from now? So we need to perform additional precision measurements. So heavy quark and jets are parts which are lacking precision right now. So we need to improve our knowledge of poorly constrained parameters. We want to study new phenomena which are quite exciting. So GEO is also one of the main the main driving forces in the analysis and interpretation of such effects, such as the calomagnetic effect. In general, effects which are related to the very strong and rich structure of the QCD vacuum, combined with magnetic fields which are created at the early stage. So the origin of collectivity, so although there are hints that point in the creation of a droplet of QGP, also in small systems, so it's not really something which, so it is a topic which is still ongoing, a discussion, debate which is still ongoing. So at lower energies, the critical point in the QCD phase diagram, this is something which is ongoing. And for me, what I like to work on, and I started a bit, is the connection with gravitational wave physics. So how does QCD matter behave at large values of baryochemical potential? So overall, if you ask me to constrain this into one picture, so the question that kind of keeps me awake at night, enthusiastically awake, is how can we discover the proper microscopic picture that describes the macroscopic behavior of the quark-gluon plasma. Now for this, so there are a number of new heavy ion physics programs at lower energies with NIKA, MPD detector, at FAIR, with the CBM detector. These are collision energies, very, very small in center of mass energy, and are supposed to look at baryon-rich environments. At RIC energies, intermediate energies of the order of 100, 200 GeV, there's Phoenix, which is expected to start taking data beyond 2023. So at the LHC, we did have our share of upgrades now during the long shutdown. We will have a new set of upgrades in 2026. We continue running, and finally a new heavy ion physics program which is being proposed now for beyond RAM 4, so after 2032. You can find details in this archive document there. And with this, I think I really ran out of time. I would like to thank you for your attention. Chige, you didn't interrupt me.